Hi, everyone. I'm Arjun. Today I'm here to talk about hypothesis testing of the independence of irrelevant alternatives in discrete choice. I'll be talking about joint work with Johan Ugander. But before I start, I want to say that I'm honored that all of you were able to join me, especially given that you're skipping a big part of breakfast. I really appreciate it. Yeah, before we get started, let's talk about what discrete choice is. It's data of the form where an item X is chosen from a set C, where C is a subset of a bigger universe of n alternatives. So while that's abstract, these types of problems show up everywhere. Consider Jenny's ice cream, which has more than 25 different flavors, but your local Whole Foods probably only stocks 5. So if you were to go shop there, that's all you'd have to select from. Now, maybe something more relevant to you is Netflix. Netflix has tens of thousands of movies in its inventory, but you often look at a very, very small subset of that before making a selection. More importantly, this problem shows up everywhere within machine learning. Consider inverse reinforcement learning or search engine ranking or recommender systems. In all these cases, you are attempting to infer preferences or value functions from over actions or items from the choices that individuals make. Interesting is that in all of these settings, one of the prevailing assumptions that's used is the multinomial logit model. It's sort of talked about as applying just a softmax over a set of items in a field like reinforcement learning. But implicit about this model and the assumption that it makes is independence of irrelevant alternatives, which effectively says that your pairwise preferences over two items don't change when you have other items involved. The interesting thing about this is that it can't account for the sort of behavioral economics anomalies that have been identified over the last 50 years. Consider the compromise effect, or how Starbucks has managed to sell you more coffee over the last few decades. When given a choice between a small coffee and a medium coffee, people have a tendency to prefer the smaller option. But when given a triplet choice, a choice between small, medium, and large, people have a tendency to lean towards the medium option. An IAA satisfying model cannot model this properly. But these sorts of effects go beyond just storied examples. Recent findings have been in search engine advertising and in web search rankings. There are an explosion of new online choice domains, and the question of whether IIA holds is a very pertinent one given the identification of all these effects. And that's the question that we ask. Can we hypothesis test IIA? But why hypothesis testing? From a practical standpoint, they provide an objective measure of inference. They're very interpretable in that when you reject the null at a particular false positive rate, that tells you that gives you a very precise control over this statistic. They're also very transparent. When you report a p-value and when you actually do it right, people can use their subjective preferences, their tolerance for false positive risk in assessing your statistic. But more importantly, it's a starting point for understanding the theoretical behavior of statistical problems, especially high dimensional ones. For example, consider recent results in discrete distributions from examples are Valiant in 17 and Acharya in 2015. Very, very cool work. If you haven't seen it, I highly recommend it. But basically, they show there that property testing, hypothesis testing of particular properties of discrete distributions require far, far few samples, especially when the samples are a function of the dimension, than actually estimating and understanding the distribution. So from a practical standpoint, if we can understand properly the testing problem, we can do it well before traditional sample requirements for estimation problems, and it could make it practically useful. This question of whether we could test IIA is actually a very old problem. Luce himself considered it in 1959 when looking at a simple two-alternative case. But over the years, there have been many formal proposals. In 1996 and in 2007, these things sort of got muddy when people reported that a majority of existing tests are insufficient, they don't work, they have very poor size properties, they're all very inconsistent. This has largely influenced a negative folklore about IIA testing. People think that there are a lot of samples required to test the problem, that existing tests are not useful, that they don't do it correctly. One person even went out as far as saying that they can't recommend these tests to anyone. A lot of this comes from not understanding the structure of the problem, where it turns out that some of the difficulties of the problem don't have to do anything with the tests that have been proposed, but rather the problem itself. And understanding the structure of the problem reveals room for where things are pessimistic and where things are optimistic. To think about this problem, it's very tied and connected to this notion of the Anna-Karenina principle in high-dimensional hypothesis testing, in high-dimensional statistics more generally, where it says that while a null can be represented by a simple model, in this case, our IIA model can be represented by a simple set of n numbers, utilities over items, the number of ways that one can deviate from IIA are many. In discrete choice, one could have arbitrary preferences, for example, over every single subset of a particular universe of items, and this could create a combinatorial number of ways to deviate from IIA. If you are attempting to test things in this setting, you are sure to fail. But this style of intuition is very informal and vague and can't be formalized. More importantly, it's been missed broadly in the literature because of the statistical perspective that researchers have taken mostly towards this problem. The statistical perspective is in classical asymptotics, where they have fixed cells assumptions. A problem dimension stays fixed as the sample size goes to infinity, and this largely leads to conclusions like likelihood ratio tests are optimal, limiting distributions exist. But in practice, in most discrete choice settings, n is very small, especially when we identify correctly what the dimension is. High-dimensional asymptotics is one approach to this problem, but it turns out that for our problem, that approach, for specifically the discrete choice problem, that approach doesn't make sense, largely because discrete choice fundamentally has a graphical comparison structure. Every data set has a set of choices that are made from subsets of items, which are all related to each other. And figuring out how to grow that dimensionally, asymptotically, is unclear and is very limiting. So we focus on finite sample analysis. We extend a lot of the recent and exciting developments that have happened throughout theoretical computer science, statistics, and information theory in testing of discrete distributions, in showing that there are scenarios in which testing distributions is far, far easier. And we also use this style of analysis to reveal exactly what is fundamental and what is impossible about the IIA testing problem and where to go as far as practitioners are concerned next. The downside of using, the upside of using our finite sample approach is that the comparison structure doesn't disappear. It gives us a guidance on how many samples are necessary to perform a test reasonably well, and it also reveals the special interaction between comparison structure, special interaction between what exactly the dimension is of the IIA testing problem. The downside is that the lower bound is analytically very thorny. And we've had to make a couple limiting assumptions that ended up being not so limiting in order to perform the analysis. And also currently we have no achievable procedure that achieves our lower bound, and that's room for exciting future work. So what is the relevant testing dimension? Before we get into discrete choice and independence of irrelevant alternatives, let's ask a simpler question of just independence testing, the property of whether an outcome space can be reduced into a low-dimensional product of two independent distributions. So let's look at two random discrete variables, x and y, with m and n states respectively. They have a joint distribution, this m by n grid. So even though the null model can be represented as this low-dimensional object, m plus n parameters, in saying that the grid is just defined by the product distribution of two multinomials, the space of alternatives is very large here. It occupies the entire grid. And that's sort of the main concept. When attempting to create an accurate low error test for this setting, a tester needs to be able to search for every point in this grid in order to verify that, in order to answer the question of whether the distribution is independent or not, because it only takes one point in the grid to be off from the representation for independence to no longer hold. So we can sort of extend this analogy towards discrete choice. Discrete choice looks at subsets. We have that listed here as C, where this grid is no longer a strict square grid, but it's more a lattice because there are subsets. And so I've grayed out some of the areas to think about this. So if you look at the vertical row as some sort of probabilistic weightings on each subset, how likely they are to appear in a choice set, and if you look at the columns as the item utility parameters, IIA is the simple low-dimensional representation. It's linear in the number of parameters, but important is that the full space of parameters, right, comes from all of the elements here. It's the sum of the cardinalities of every subset in consideration. The more subsets that you consider, the harder this problem gets because there are more ways to deviate from IIA and more things to study. So we define this problem as this hypothesis testing problem where we look at this choice system object, weightings over choice sets by the probabilities of items being chosen from choice sets as the system of interest, and IIA constraining that system as defining it as a normalized ratio of item utilities. And so we have notation here, script cal p IIA and script cal p to distinguish the two subsets. So of course, the last major detail when considering any hypothesis testing problem is the notion of separation. When I say I'm testing IIA versus not IIA, that distinction isn't immediately sharp, especially when you're thinking about it in terms of finite samples. Where instead of looking at that problem, we have to say it's IIA or it's something that is a little bit outside of the set of IIA, where the metric that we use to define what is a little bit outside is total variation distance. Why we use total variation distance? Well, it's highly interpretable, and there's a bound on total variation distance. There's a bound on every event occurrence. But more importantly, it connects it into this broad and exciting literature across multiple fields on discrete hypothesis testing and shows where there's room to get cool results for this econometrically motivated problem. And how that ties into other properties of discrete distribution. So our actual testing problem looks at a delta separation by the total variation metric from the set of IIA. Thinking about visualizing separation, I know most of you are still thinking about breakfast, so this analogy might be a good one where the set of IIA is inside the yolk, whereas what we're testing it against is things outside the egg. So the egg white is sort of our separation region. It's this like region of indifference where an error is not necessarily serious. Of course, this separation metric, especially in total variation, is highly non-convex, so don't let the egg mislead you. The important structural object in our analysis is the comparison incidence graph. So specifically on the left here, we have item nodes. On the right here, we have set nodes. And what's connecting them, the edges in this graph, is the denotes membership. One of the main assumptions that we make throughout our work is that every item appears an even number of times across all of the sets, and every set is of even size. Thinking about this graphically, it means that every node in this bipartite graph is of even degree, which means that the graph is Eulerian by definition. So a recurring example that we'll look at is the set of all pairs of size 4, and then also a set of 4 as well. That creates an Eulerian graph. This comparison incidence graph will be very important in how we study this problem. Lastly, the notion of error that I've been talking about is risk. Specifically, it's the sum of type 1 and type 2 errors. There's also a neat interpretation of this in terms of level alpha tests. If you're curious, do look at the paper. But we're basically looking at the worst case error of a particular test. Why we do this is because it provides a level playing field for analyzing tests. Some tests can be good at detecting certain types of violations while others can. So it's good to sort of look at worst case style analysis of what a test can do. And we're not focusing on any particular testing procedure. We're focusing on the fundamentals of the problem. We're actually looking to lower bound the risk of the best possible tester one could ever hope for. And so this gets us to our main result where we have a lower bound on the minimax risk. Important are two problem parameters, mu sigma and alpha sigma, that I'll get to and explain, that connect it very closely to the graphical comparison structure of the IIA problem. Otherwise, the neat thing here is that this bound looks very similar to a result that's been derived by Valiant and Valiant for testing discrete distributions in saying that the dimension is only square root dependent on the number of samples. So there are certain scenarios in which if you can control the problem dimension properly, you don't need samples on the order of dimension to do tests. I'll make this formal by considering two specific cases. But before I get into that, I want to point out that we don't have to have problem dependent parameters. They can be loosely upper bounded by the number of items, and this upper bound doesn't end up being loose because a lot of the times D ends up being exponential. So the high-level consequences, the big takeaways, are first, the major pessimistic takeaway. IIA as a general testing problem philosophically has been considered as a property of all the subsets of a particular set of universe. And when you're attempting to test for that, there are an exponential number of different subsets, and it means that all tests for this property will have a worst case error of a half, so the error of a random coin flip, until the number of samples you have are exponential in the number of items. So effectively, the true property testing of IIA is impossible. And we show this lower bound by just looking at the setting of all even subsets, because that's how we get Eulerian Eulerian comparison graphs. But lower bound on all even subsets is, of course, the lower bound on the all subsets problem. And this sort of formalizes why people have been so pessimistic about the IAA testing problem, why these tests haven't worked. It's because people have not tried to control what sets that they're looking at, and are rather just loosely applying IAA testing procedures. And this approach will never work. This approach is doomed to fail. But understanding the structure then allows us to look for optimistic next steps. Analyzing our lower bound more closely for the setting of all pairs reveals something interesting, that, as I was saying before, the number of samples only scale sublinearly with the dimension, specifically square root of the dimension. And so when looking at the setting of all pairwise comparisons, a fairly important setting in the context of matchups and in the context of competition modeling as well, you only need samples linear in the number of players, which says that you can get away, you can study the whole set of pairwise comparisons with far fewer samples than you would expect. And this is sort of consistent with the Anna-Karenina principle that I talked about earlier. Okay, I think, never mind, a slide got skipped. Basically, this sort of thing is consistent with the idea that when you're restricting the number of irrationalities that you're testing against, when you're restricting the number of alternatives, you can do reasonable things. And the discrete testing problem of IAA is special in that you can do very interesting things. Lastly, we consider a very simple cycle where analyzing our lower bound reveals a potential for a fully dimension-free test setting. So if you look at a simple cycle of n items, this says that the complexity of the lower bound is actually fully independent of n. N can be arbitrarily large, and you only need a small number of samples to test. This is one of the benefits of understanding structure, because what this practically says is when you're in these extremely low sample settings and you're trying to identify whether IAA is a good model or not, you can apply your researcher prior by sort of selecting a simple cycle among n items and only performing your test there. So I'll briefly run through the details of how we approach this problem and where the graphical connections exist, where we look at this separation problem, this figure to the right on top that I showed you earlier, and what we have there is we turn that problem by reducing it as a comparison from the uniform distribution. The uniform distribution sits within IAA and is complicated enough to model all the complexities within IAA, and then we compare it against we compare it against a set of exponential number of alternatives that we carefully construct. It turns out that how we perturb and construct these alternatives that live outside of IIA involves satisfying two constraints about how we perturb it. Specifically, that all the perturbations are normalized across every single set, so perturbations can't have any net movement across any set in this probability space, and then also they're not normalized across item appearances. And it turns out that this has a very graphical interpretation, that they're Eulerian orientations of the comparison graph. So we can take advantage of this and construct an exponential number by creating a cycle decomposition of our comparison graph and by rotating every cycle arbitrarily to create an exponential number of these perturbations. The rest is applying Lacombe's method for binary hypothesis tests, but the big experimental intuitions here are that our structural understanding reveals that there's sort of this trade-off. We can apply researcher priors and study small sample settings, where normally we'd want to broaden the scope of our test, but this problem is so combinatorially complex that narrowing the scope of the test is the valuable thing to do. So the global lower bound is exponential, the pair's lower bound ends up scaling linearly in the number of items, and our special case is for these very, very low sample size settings. This also lastly inspires just thinking about model-based tests in general. The tests I've talked about here are IIA versus anything goes, but carefully modeling what sort of context effects exist are the key to constructing good tests. Mostly this sort of thing has been avoided so far because good models don't exist in discrete choice. Recent work done by me and a few co-authors look at proposing statistically tractable examples and studying those. Sort of the main takeaways here are that we are generally left to wonder exactly when IIA has been rejected, since the general problem was exponentially complicated. But we hope that this work provides exciting future directions to construct an optimal procedure to achieve all of these practical instances when IIA testing can be done. And the last sort of takeaway is I like this work a lot because it connects econometrics to machine learning. It sort of brings these rigorous ideas into econometrics and then also studies econometrics in this rigorous light. Thanks.